Okay, so problem 4.53, it says find the branch currents IA through IE, and then it wants us to show that the total power generated equals the total power dissipated. So let's go ahead and I'm going to solve this using the universal method. Let's go ahead and label this. I'm going to call this node here V1 plus V2, and then call this one V3. Looks like the labeling for the current have already been made. So we can go do our KCL. So we know, well, I know that 19 plus IB equals IA plus IE. I know that IE equals IC plus ID. And I know that 2IB plus IC equals IB. Right? So got 1, 2. Yeah. So this is our KCL. Let's actually, I'm going to write down the variables missing. V2, V3, IA, IB, IC, ID, and IE. So we got 8. So we can do equation for components. IA is equal to V1 over 40. IB is equal to V2 minus V1 over 5. Know that for ID is equal to V3 minus V1. Know that, well, we know that V3 is actually negative 240. So I messed up there. I should have put that. But anyways, we can keep going. So 3, 4, 5, 6, 7. What else am I missing? Am I missing the 5? No, 4. Oh, I see. So then IC is equal to V3 minus V2 over 10. And then, yeah, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Just gonna make sure I'm doing the right thing. So yeah, 19 plus IA plus IA, IE. Okay, IA 40 V2 minus. All right, so let's go ahead and plug this into Maxima. Yeah, bring this down. 8 equals IA plus IE. E equals IC plus ID. 2 times IB equals plus IC equals IB. IA equals to 1 over 40. B equals 2 1 over 5. 4 times ID equals V3 minus V1. IC equals V3 minus 2. And then V3 equals negative 240. And so variables are V1, V2, V3, IA, IB, IC, ID, and IE. Yeah. So yeah. Let's see. So we get this. So us knowing this, now we're able to see that the total power generated equals the total power dissipated. Okay, so let's go ahead and find the power for each. I'm gonna make this separate. Okay, so power for the 19 amp source. 19 amps, and then we know that V1 is negative, so it's so this would be negative and then positive since this is our higher potential. And we want to follow well, we know that current is well, in a sense entering positive, so it's positive here, and the voltage is A1 280, right? So then we say that this 19 squared times 280 is this big number. It's 10 to 80, I believe. Or oh, what am I doing? This shouldn't. Sorry guys, brief part. That shouldn't be it. 19 times 280. Yeah. 320 watts. Okay, we're gonna use the 40 ohm resistor. So IA squared times that'd be it. It would look like this: negative and positive high potential. So if we have this would be 40 so let me look at this again. So yeah, no, that'd be right. So 49 times 40 is 1960, right? And then we got, I'll do the 5 ohm resistor one. And say IB, which is 8 squared times 5. 64 times 5 320. Then we got power of dependent voltage source. So the power of the dependent voltage source for ID. So we know that current's leaving the positive terminal, so we know it's negative. Say IE. IE is equal to 4 times ID. 40. Well, no, what am I saying? That's yeah, bringing forward again. For ID is equal to the potential across V3 minus V1. So I can just say for ID times ID. ID is 10 times IE. IE is 18. 40 times 18 negative 720. Let's do dependent current source. Okay, so it's negative, right? Positive here, right? Or it's actually since E2, yeah. So this, yeah, this would be a negative. This is lower potential here. 2 is negative 320. Current's going in, so we consider this positive. And then we have 2 times IB. IB is negative 8. Times negative, wait, or no, it'd be 0 minus negative 320, so it'd be 320. So this would generate actually power, yeah. So 16 times 320, 5120 watts. And then now we're missing the 240 volt source. So I know ID, well, we know that it's leaving the positive terminal, so we automatically know it's start with the negative side. We know ID is 10, and the voltage, you know, 0 minus negative 240 is 240, so it's generating. So negatives, we add our negatives up. Which one else is, which other one is negative 20? Oh, this one here, right? So the sum of these is 720 plus 5120 plus 2400. It's 8,240 watts negative. And then the addition of these, well, I'm gonna make these in red. It's dissipated. the addition of 5,220 or 320 plus 1960 plus 320. And well, I forgot the 10 ohm resistor, so I got ahead of myself there. The 10 ohm resistor really quick. So 10 ohm resistor is IC squared, 64 times 10, 640. Yeah. So plus this dissipated total would be this plus 640. Yeah. 8,240 watts. So the addition of 5,320 plus 1960 plus 320 plus 640 would result in this. Therefore, the total dissipation equals the total power developed here. And that concludes this problem.